Let me know whenever I should start.
Yeah, just a moment. Okay. So today's final speaker is Priyesh Chakraborty from Harvard University, and he's going to talk about Defeater as an action detector.
Um, Hello everyone. Very grateful for the opportunity to talk to you all about my work. So specifically today I'll be talking about, as Anish just said, about uh, detecting axions through primordial correlations, through how their behavior in Detector. But this is based on some work I did with John Stout, um, archive numbers over here, last year. Um, yeah. The main point I will try to convey through my talk is axion physics in De Sitter may be more subtle than previously thought. Um, so right, without let's just get started. Um, I mean, we already I wasn't present for the entirety of the previous talk, but let's just there was also an axions, but nevertheless, let's just remind ourselves why we care about axions. Um, so I mean, axions show up everywhere in high energy physics these days, anywhere from the strong CP problem, where you need the QCD axion to explain the smallness of the neutron electric dipole moment. But these axions can also be a part of the dark sector, can be a part of dark matter through the misalignment mechanism. And generically, in theories of quantum gravity, these axions are just produced in abundance. Um, there's like hundreds of them in string theories that people study. So specifically, I'll be focusing on the third kind of axions in this talk. Not so much the QCD or the QCD axion or anything about dark matter. So right. So actually, I'll be fairly general in this talk. I won't adopt any kind of fancy definition. No KSVZ, no DFSZ. But really, I mean, fundamentally, what is an axion? So an axion is just the field theoretic version of a particle on a circle. So just to say that it's a compact scalar field. It takes values inside a circle at each point in space. And this circumference of the circle is parameterized by what's commonly called the decay constant, F, for historical reasons. But really what F tells you about is the circumference about the field space of this axion. And I like to emphasize, this is really a gauge symmetry. It's not commonly conceived that way. It's not just a global symmetry, it's a gauge symmetry. Right, specifically, as I said, I'll be talking about these quantum gravity axions, where this F, this decay constant, is related in some way to the size of any extra dimensions that might exist around us. So if you know what F is, then you can constrain the size of your extra dimensions. This is something to keep in the back of your head. Right. Going back to this gauge symmetry. Right. Why is this? I mean, the reason why I'm emphasizing this gauge symmetry is because we already know that from quantum mechanics that there's a huge difference between a particle on a circle and, for example, a particle on a crystal. Like whether you choose to identify the range of your field space completely fixes the kind of states that you see. So in the particle on a circle, for the same exact potential, in both cases, for a particle on a circle, you see quantized states. And for a crystal, even though you have the same potential, you see block waves, a continuum of block waves. So this gauge symmetry, we know in general, can be really important. Like talking about this identification. But why does it not matter so much in quantum field theory in flat space? Well, that's because there's your full axion field, has a zero mode, which is spatially homogeneous, plus some non-zero modes. And this gate symmetry is seen entirely by the zero mode. But if you look at the action, the zero mode always comes dressed with this overall factor of volume. And in the infinite volume limit, this mode just freezes out from dynamics. It doesn't participate in correlation functions. So that's why in naive like correlation functions in quantum field theory, this in flat space quantum field theory, this gate symmetry is not so important. So we don't necessarily need to care about it that much. So how do we typically try to detect it in flat space situations? Well, we can observe states which are charged under this gate symmetry, strings, as the previous talk was talking about. But for stringy axions, the tension of these strings can easily be quite large. So of order like f times f Planck, m Planck. And they might never be produced. These stringy axions, they might never be produced. Or maybe there's some clever mechanism to make them more observable. But this is one way you could probe it in flat space. So the main question for us is there some other way? Whoops, my screen was covering some of the text. Anyway, so can we find some other way of telling that this field is indeed compact and not just like a crystal, something which has a periodic potential but not actually seeing a compact field space? And one of the key intuitions we'll carry with us is that some of this logic that I just gave you about the zero mode freezing out in the infinite volume limit may not apply in Detector for during inflation, because Detector is kind of like a finite. It's kind of like a box. It has an IR horizon, which is given by the Hubble scale. So maybe this zero mode doesn't quite freeze out in Detector. Maybe it's important. So this will be the main question. Can any primordial observables, by primordial I specifically mean inflationary observables, help us to constrain F? This is the question we'll be carrying with us. And my goal for the rest of the talk will be isolating whether this will be telling, well, the answer is positive, but we'll be addressing how it shows up in the so-called cosmological collider signal. I'll explain what that means in case you are not familiar with this. And I'll show that indeed, like a compact scalar, something which has this phi to 2 pi f identification, and something which does not, so non-compact scalar, will lead to different predictions for in the cosmological collider. Before I move on, are there any questions? By the way, I forgot to mention, but feel free to stop me anytime to ask questions. No need to wait till the end.
Are you assuming that the gate symmetries that for the axion, let's say, are abelian or non-abelian, or can they be non-abelian?
So this is very definitely abelian.
Yeah.
There's nothing non-abelian going on over here. I'm not sure. I've never thought about. I mean, maybe I don't think you can have a non-abelian gate symmetry for these, like a non-abelian periodicity.
What I mean is, we know that string theories have a lot of underlying, when you compactify them, a lot of non-abelian, even discrete gauge symmetries, right? Which can behave like a Pecek-Quinn symmetry, but anyway, doesn't matter. Don't worry about it.
That's an interesting question. I just never thought about it. But yeah, maybe food for thought. What happens if this is somehow non-abelian? Anyway, thank you for the question. Is there any other questions so far before I move on to? Okay, then I'll just move on. Okay, so what is this cosmological collider signal? So, under standard inflationary paradigm, we know that the CMB maps, galaxy maps, they're all seeded by uh, primordial fluctuations of something we call the infraton, which is related to what I call this zeta over here, some fluctuations of some infraton field. And this, under the standard paradigm, I'll be working throughout under the single field slow roll paradigm. This the fluctuations of this infraton will in turns, will have some width. Will have some variance, which will, leads to the scale invariant CMB and matter power spectrum. But in principle, this infraton or this gauge invariant mode zeta could be interacting in during inflation. So this is a cartoon over here where specifically this zeta could have been coupled to some heavy degree of freedom, some spectator particle sigma, and this coupling will produce like a specific kind of 3-point correlation function in both the CMB and LSS data. So and there's a lot of theoretical work that's been going into understanding what these signals could be, what their phenomenology is. Formally, what do they tell us about physics in etc. But and also towards measurement. So just I would like to emphasize that recently these signals have been constrained using the CMB and LSS data as well. So people really want to measure this soon. Right. So in the cosmological collider signal, so what is it? Some exchange of some heavy degree of freedom in the bulk of the inflationary space of some massive particle sigma. So this instead of the mass, I'll often be referring to this new parameter which keeps track of the mass. Specifically over here, this m sigma over h will be larger than 3/2 for technical reasons. Now, where it does one characteristic aspect of the signal is as you take one of the momenta, so in this case k3, if you send it to 0, you're also sending the momentum of this propagating particle to 0. In other words, you're setting it on shell, and in long distances, the sigma particle will oscillate through space. And these oscillations get imprinted onto the 3-point correlation function. So in the 3-point correlation function, as I send k3 to 0, you see these characteristic oscillations where the frequency is set by the mass of the particle. So you measure the frequency, you measure the mass of this particle, and there's also this overall decay, this factor of k3 over k1, and this exponent of 1/2 is, in this case, is entirely just set by geometry, by Hubble dilution. So the fact that when the sigma particle propagates through exponentially expanding space-time, it gets diluted, and this dilution leads to this factor of this exponent of 1/2. Right. If you introduce some decay channel for the sigma particle, if it interacts with some other stuff, then obviously this decay will get enhanced. And this enhancement is captured by what we know as the anomalous dimension of the particle. Right. So essentially, yeah, if it couples to other stuff during inflation, even if it's like a self-interacting particle, you give it some decay channel, you will know, you can infer its existence through a measurement of the decay exponent. And if you find that it differs from 1/2, then it decays. So I'll be focusing on this anomalous dimension specifically. And our main goal for this exercise will be to see, okay, if I couple the sigma to a compact scalar, an axion, versus a non-compact scalar, do I get any qualitatively different predictions or not? And well, I mean, we do that, otherwise I wouldn't have written a paper on it. Right. And just to note, like, I've kept factors of Hubble over here. Usually I will be very cavalier about factors of Hubble. So if you see something like m squared floating around, like m squared plus 1 or something, I've set Hubble to 1, so it should be m squared over 8 squared. So it's just a note. Right. So right, many of the calculations involved are through slightly not traditional methods. So at any point, if you have any questions, please feel free to stop me. But yeah, just to give you a sense of how these things are calculated, because that is itself an interesting topic. What we want to do effectively is compute an interacting two-point function in Detector, and we want to extract its leading behavior in the infrared. And the way we'll do that is by analytic continuation. When you analytically continue the setter, it becomes a sphere. So we'll be calculating correlation functions on the sphere, and carefully analytically continuing our results onto Lorentzian signature. Right. So we're dealing with two-point functions in the setter. We should exploit the symmetries available to us, and the setter symmetry, like the setter invariance, basically translates into rotational invariance on the sphere. So any two-point correlation function will be a function of the angle subtended by 2 points on the sphere. Specifically, it'll be useful to keep track of the cosine of this angle, which I'll call C. And this is really analogous to your standard Poincare invariant distance in flat space. On the sphere, of course, this C is a cosine. It only takes values between -1 and 1. But I can phrase my analytic continuation in terms of continuing in this variable C onto the entire real line. And specifically, I'm interested in the IR. So that corresponds to sending C to -infinity. So how is this done? Well, let me just remind you, everybody knows this already, but let me just remind you that how the stuff like this is accomplished in flat space. I mean, you do something similar in flat space as well, right? Like when you analytically continue x minus y squared onto Euclidean signature, this can only be positive, but is positive definite, or positive semi, whatever. But in Lorentzian signature, this can also take on negative values for time, which corresponds to time like separated points. So it's something very similar is happening in this term. Sorry, actually, I'll just drink some water. Something very similar is happening in the setter. Anyway, so in flat space, how do we infer the long distance limit from of your two-point function? Well, usually you find what the momentum representation of your propagator is, 1 over k squared plus m squared. It has two poles corresponding to the mass, and the location of these poles like fix what your long distance behavior is going to be, and it's just exponential in flat space. But the important thing is it's the poles of your propagator, of your momentum space propagator. Well, what is momentum space on the sphere? It's something like angular momentum. So any two-point function can be expanded in terms of, well, I'll be working in d dimensions, so d-dimensional spherical harmonics, and also I'll often keep track of the number of dimensions using alpha. So alpha equals 3/2 is the same as d equals 4. Right. And so this expansion in terms of spherical harmonics, the coefficients which keep track of it these are what I'll call the momentum coefficients, and they this will be basically analogous to 1 over k squared plus m squared. Right. So you have some expansion determined by the total angular momentum, magnetic quantum numbers. You sum over the magnetic quantum numbers, and you get something which is manifestly de Sitter invariant. So this is the Cj of alpha. These are called Gegenbauer polynomials. So it's the d-dimensional version of your Legendre polynomials that people are already familiar with. So nothing fancy going on over here. But specifically, the poles of your momentum coefficients in J are what are going to determine your long distance behavior. Now, of course, like one caveat, just to note, like when I said analytically continue, I mean you could say, okay, I just have to I could just evaluate the sum for Lorentzian separations as well. For example, setting C to -10. Sadly, that doesn't work. You have to be more careful about how you analytically continue it. I won't go into details, but of course, happy to talk about it after. Right. So for the free theory, what are these momentum coefficients? So again, you have some massive particle sigma. You can just calculate what these momentum coefficients are going to be. And they look basically like, as I said, it's something like 1 over k squared plus m squared. Except because we're on the sphere, it's j plus 2 alpha. But this propagator can be organized into a set of 2 poles, what I'll call the scaling dimensions of the field. So delta sigma and the so-called shadow scaling dimension, delta bar. It's defined in this way. And these 2 poles are going to fix what my long distance behavior are going to be. And in de Sitter, it's a power law instead of an exponential, which is important. And these 2 poles are going to fix what my exponents are going to be. At this point, I'll just find it useful to note that, as I said before, like I'll be distinguishing between something which is heavy and something which is light, depending on whether the mass is larger than or smaller than alpha. So just a reminder, alpha is 3 halves in 4 dimensions. So for a sphere, if your particle is heavy, and scaling dimension has real parts, alpha plus I nu, where this nu is the same mass parameter that we saw before. And in the infrared, we'll find that this thing decays at the rate set by alpha, just fixed by the number of dimensions, and some part which oscillates, 2 frequencies, but same frequency, complex conjugates. Right, and just a reminder, so alpha is again 3 halves, and this 3 halves is exactly responsible for the factor of 1/2 that we were seeing in the 3-point function of the infraton. So on the other hand, light fields, when the mass is smaller than alpha, then the leading infrared behavior is just set by 1 pole, by just the scaling dimension, not the shadow, and the field will just decay at infinity. So there's no oscillations. So that's why these 2 are distinguished as the principal and the complementary series on de Sitter. Okay. Wait, I guess any questions at this point? This is setting the stage for the free theory. Now we'll move on and talk about the differences and at the level of the free theory between the compact and non-compact scalar. Very well. Let's move on. So first, now let's talk about the non-compact scalar. So let's consider a massive particle phi. And as I said, we'll be talking about light we'll be talking about these particles in the light limit. So in the limit where m phi goes to 0, and try to see if there's some difference. So let's see what happens at the free theory for a light non-compact scalar. It's specifically useful to focus on the zero mode. So phi of x on the sphere is some j equals 0 mode plus j not equals to 0. All the other my y's and phi's are resembling one another, but I hope that's clear. So there's some completely isotropic j equals 0 mode and all of the other non-zero modes. So it's useful to focus on just the zero mode over here. So in this plot over here in blue, what I'm plotting is the potential or the action for the zero mode. So the zero mode doesn't see a kinetic piece because it's isotropic. What it only sees is the potential. And it's just quadratic over here. And in red, what I'm plotting is exponential of minus the action of phi 0, which is just, in this case, is just a Gaussian. It's the thing which weights the zero mode in the path integral. So as we can see, as I make the mass lighter, the potential becomes broader, and this weighting in the path integral, or equivalently the state, the wave function for the zero mode, becomes broader, which means that like its fluctuations, the zero mode fluctuations become larger and larger. It's the variance of which is just fixed by the variance of the state. So the 2-point correlation function reflects this. There's this zero mode contribution that I've isolated, which goes as 1 over m phi squared. So it's singular as you send m phi to 0. And this is very important. There's actually an old paper by Allen, which identifies this. Says what this basically signifies is that you can't really have master scalar fields, spectator scalar fields in the sitter. They're pathological. So something dramatic has to happen when you take a theory and send the mass to 0 exactly. But what about the compact scalar? So over here, I found it convenient to just scale out this factor of f. So the periodicity is just 2 pi in this case. Well, over here, I can just send the mass exactly to 0. Even though the zero mode potential is 0, like it's flat everywhere, there's no potential. The field is always bounded in field space. So the zero mode fluctuations, they cannot blow up. That because phi 0 cannot blow up. The only reason in the previous case we saw a divergence in the massless limit is because phi 0 could just take values anywhere on the real line, right? Like it could be as large as you want. It's completely unconstrained. But over here, being unconstrained is not a problem. Phi 0 in the massless limit, the zero mode fluctuations just become some number. So the propagator is still well defined, which is a huge difference between the two cases. So for instance, so in the unfortunately though, even though the propagator is not singular anymore, what it still does in 4 dimensions, what the zero mode, what this compact scalar propagator looks like is this piece, this 1 over c piece, plus a log. So the 1 over c piece is really, it's the same as having a 1 over r squared term. So it's similar to, it's almost the same thing as having a massless massless propagator in flat space, but with this log piece which grows in the infrared. So this is as if you had some log r squared piece. which people familiar with two-dimensional quantum field theory will recognize. It's very similar to what happens in 2 dimensions in flat space. So what this, and as in 2-dimensional flat space, what this is telling you is that this phi propagator is bad because it grows, it doesn't decay in the infrared. So it plagues your perturbation theory, introduces a bunch of infrared divergences. But in the compact scalars case, I mean, this is kind of expected, right? As I said, phi has a phi plus 2 pi gauge symmetry. So phi correlator is not a gauge invariant. The phi is not a gauge invariant operator. So what we should really be doing is working with genuine gauge invariant operators. So one option would be d mu phi, but this is not very interesting. It just kills the zero mode. What's more interesting is these so-called vertex operators, which are exponentials of phi. And if you compute the 2-point correlation function of these vertex operators, you find that these do decay at infinity. And this decay rate in 4 dimensions is this is what I'll call beta. It decays, and this decay rate is set by ratio of Hubble over F squared. So yeah, physics is very different now for a compact scalar field, right? You have to work with these gauge invariant operators and the behavior in the infrared, like even the massless limit is not set by the mass or anything at all. It's only set by this important ratio, because now you have this other scale that you have this other scale F, which has to enter physics in some way. So it makes sense that the ratio of Hubble over F would show up in this way. And just an important point, like this beta can be in principle as large as you want. So it can decay faster than any free field. Previously we saw that the fastest a free field can decay is c to the minus 3/2. It's set by 3/2, but beta can be larger than 3/2 easily. But importantly, okay, as I send F to infinity, I should recover the dynamics of a massless of a light compact scalar as well, because F is much larger than Hubble. Now, if we invoke this, if we invoke this logic of the Starobinsky picture, the stochastic inflation, we imagine this field phi exhibiting a random walk on like infrared scales. It's just getting kicked around by Hubble size fluctuations. If F is really large, then this particle should never learn that it's actually compact, because it should never, like, if you imagine just like on a circle, this phi particle is getting kicked around randomly, it will take a lot of time for this particle to learn that it's getting kicked around by Hubble size kicks. It will take a lot of time for this particle to learn that it actually lives in a finite field space. So indeed, as I send F to be really large, beta is small, and its decay is going to be, like it's going to be minus c raised to some negative of some small number, which is indistinguishable from having, as I mentioned before, the decay of a light particle in de Sitter. And we'll keep appealing to this kind of logic. Okay, just an aside, but the singularity in the light non-compact propagator that we just found, it really has profound, as I said, it has really profound implications for physics in de Sitter, because of this infrared divergence. I mean, there's this famous story of Starobinsky, Starobinsky formalism as being some sort of like, when you send this mass to zero, you're really approaching some kind of non-perturbative limit, and you have to do a bunch of resummations. So there's this rich history of infrared divergences in de Sitter tied to exactly this type, this 1/m² divergence that we saw in the propagator. It's tied to other stuff like the absence of spontaneous symmetry breaking in de Sitter as well. Whereas for the compact scalar, okay, we don't see this divergence. So what happens? Let's try to find out. So right, that was after discussing free theory. Let's go back to the question we actually care about. We want to compute the decay width of sigma by coupling it to a light non-compact and light compact scalar. Right. So let's do the non-compact scalar first. I think an example, we'll just couple it to sigma through a quartic vortex. It's as a leading order coupling, and we can just calculate what the decay width is going to be. So the leading order. So what we have to do is calculate. As usual in that as is like familiar from flat space, we just calculate the self energy. Imaginary part of the self energy is going to determine what your anomalous dimension is, and the leading order self energy in this case is going to be set by this sunset diagram at 2 loops. And so we can go through the standard procedure and find that the anomalous dimension in the leading contribution to the anomalous dimension in the limit where m∫ goes to 0 is given by this remarkably simple expression. So it's fortunate for us. Now there's 2 main observations about this anomalous dimension. One thing is the square of something, so it's positive. It's always going to be positive. And the second is that it's severely infrared enhanced. So I send the mass to 0. As you can see, like I can't send the mass exactly to 0. It's again the same consequence. It's just the same, infrared blow up that we were seeing before. So yeah, as you can see, it's severely infrared enhanced. So for a light particle, it's going to be this anomalous dimension is going to be quite large. So 2 main observations. Yeah. So in the cosmological collider signal, just to remind you, this anomalous dimension appears as an additional contribution to the decay piece. And it's always going to cause like a faster rate of decay and can easily be quite large. I mean, subject to perturbativity requirements, of course. But it can easily be like an order 1, order 10 number. So let's go to the compact scalar now. Now, as I said, compact scalar gauge invariant, you need to couple it to sigma using some gauge invariant operators. So we pick a cosine. I mean, this is why we had used the quartic vortex in the previous situation, because expanding this cosine out will at leading order give you something like sigma square phi squared. Anyway, so in this case, let's consider the full resum potential. Like you have a full cosine. So also, yeah, I found it useful to go back to the dimension full axion over here. So f appears in this cosine. There's no f over here. So the leading order anomalous dimension is going to be determined by the so-called bubble diagram. I mean, don't be fooled. It's not actually a bubble diagram. This should really be understood as like, you're exchanging a phi, you're exchanging 2 phis, 3 phis. So you're in some sense resumming, infinite exchanges of phi. But it's convenient to capture that by just exchanging a single composite operator, this vertex operator. So yeah, so as I had mentioned before, now in the compact scalar case, we have an additional scale. We have f, or another dimensionless ratio, I should say, f over h, which can control physics. And as I said before, when you send f over h to infinity, where it becomes very difficult for this axion to really learn that it's a compact scalar, we should reproduce the same effects as before. But when f over h is order 1, then anything can happen. So this is a plot of the anomalous dimension when f over h goes to infinity, so in this so-called non-compact limit. As you can see, this number can be quite large. But quality, I mean, don't worry about the numeric. But approximately it behaves something like this. It just scales as 1 over beta. So just a reminder, f over h going to infinity is like beta going to 0. So it's singular as you send beta to 0. And as you can see, it's always going to be positive. So this is for some choice of the mass of sigma. So it satisfies the 2 criteria that we saw before. It's infrared enhanced and it's large and positive. So it behaves, so its effect is going to be indistinguishable from a non-compact scalar. But what happens when you send f over h to 0 or beta to infinity? Well, then qualitatively, again, you can ignore the numeric, but approximately it behaves something like this. It has oscillations in beta, some fixed frequency, and it has some decay, some exponential decay. Well, the exponential decay makes a lot of sense, right? As I said, the 2-point correlation function of these vertex operators went as minus c to minus beta in the infrared, or 1 over r squared to raised to beta. So as I made beta really large, this 2-point correlation function decays very fast. So it becomes difficult for it to propagate any information. So it behaves almost like an extremely heavy particle. So its effects on the heavy particle sigma should be diminished. And that's what we see, it's exponentially diminished. But the interesting thing is that we find that these oscillations, on the other hand, can cause this anomalous dimension to be negative as well, which is not something you can ever see in flat space, right? Because you're always constrained by the optical theorem to be to always have positive anomalous dimensions or positive decay widths. But over here, we're seeing that it's possible for the anomalous dimension to also be negative. And what that means phenomenologically is that it can cause the sigma particle to decay slower than the free field rate. And this is the main point. So currently, there's just no other way we know to generate a negative anomalous dimension. So tomorrow, if people do an experiment, people finally release mega mapper or something, and people look for this cosmological collider signal, look for the decay width, and find a negative value for this anomalous dimension. Currently, the only explanation could be an active axion in the early universe. And this is my main point. As I said, as I advertised, compact scalars, if you take their gauge symmetry seriously, can produce qualitatively different effects in de Sitter. Okay, so where do we go from this? So as I said, you can see these oscillations in the anomalous dimension. But the way that we calculated them is rather opaque and makes some of the physics not as manifest. So, is that for example, a cleaner way to understand why these oscillations are occurring, like what is physically happening for this to occur. So there's some work in progress in this direction that I have ongoing with Tim Cohen, Dan Green, and Yuan Wang. There's some other detection channel that we could also study with these vertex for this axion involving these vertex operators. So for instance, I could ask about, well, I'll just write out the whole thing. We could ask, like, during inflation, I could have a 3-point function generated by just the exchange of a vertex operator. What does that look like? Hopefully I will release a paper on this soon, within the next month or so. Finally, as I said, we're working in like single field slow roll, very like this in the de Sitter limit. And so in this exchange, we didn't really care that much about the fact that we were in inflation, which is the standard case when you calculate things in single field slow roll. But for an axion, you could ask, for instance, what if during inflation this decay constant changes in time? There are ways to engineer that. What if the axion model is more realistic? Currently, it's really just a toy example. So yeah, these are some future directions in which we're carrying out work.